Hello, my dear students. I'm Shrikala, the faculty from the Department of Mechanical Engineering, Global Academy of Technology. Today, in this lecture, we are going to solve some of the numericals on the fins. Before getting into the numericals, let us see what is efficiency and effectiveness of the fin. Efficiency of the fin is defined as the ratio of actual heat transferred by the fin to the maximum possible heat that can be transferred by the fin if the whole fin surface area is maintained at the base temperature. That means this heat transfer would be maximum with this condition. So if we consider for an infinitely long fin, efficiency of the fin is given by square root of HPKA into TB minus T infinity. This is the expression for the heat transfer from a fin of infinite length. Now, for any heat transfer by convection is given by the formula Q equals H into A into delta T. So substituting in the same way, H into area, surface area of the fin. So this surface area of the fin is given by perimeter of the fin multiplied by length of the fin. So H into P into L multiplied by the temperature difference between the fin and the atmosphere. So now here in the fin temperature, we are keeping it at the base temperature. So writing it as TB minus T infinity, it is atmospheric temperature, and reducing this, we'll get the expression for the efficiency for an infinite long fin as 1 by ml. Similarly, if we substitute it and do it for an insulated tip, we'll get it as tan hyperbolic ml divided by m into n. Now, coming to the effectiveness of the fin, this is the ratio of the fin heat transfer rate to the heat transfer rate when there is no fin. So the rate of heat transfer with fin in case of infinitely long fin, as said in the previous case, is square root of HPKACS into TB minus T infinity. And without fin, we are writing it as H into A is A into TB minus T infinity. So it is given by this expression. So for a straight fin, so P by ACS, if we just write it as perimeter is nothing but 2 into P plus Y, cross section area is B into Y, you will get it as 2 by Y. So this effectiveness will, if this effectiveness is greater than 1, then there is improvement in the rate of heat transfer using the fin. If this effectiveness is less than 1, that means without fin itself, the rate of heat transfer will be more. So these are just the conditions which is given with respect to the values of P, K, H and ACS. So if K is large, then effectiveness will be more. Similarly, if H is small, effectiveness will be higher. Now, in this sheet, I'm just giving the copy of the data handbook having the fins as the sheet. So in this, we have different columns. First column gives the type of the fin. So it is long fin, short fin, end insulated, end short fin, end not insulated, and if at the end the temperature is specified. So these are the different cases specified. And the next column gives the temperature distribution. T minus T infinity divided by TB minus T infinity. T is the temperature of the fin at any length on the fin. T infinity is the atmospheric temperature. TB is the base temperature, and again T infinity. So for a long fin, it is given by e power of minus mx. For a short fin, end insulated is given by cos hyperbolic m into L minus x divided by cos hyperbolic ml. And for the short fin, end not insulated, given by this big expression, and at the end having certain temperatures given by this expression. Similarly, the heat transferred by the fin Q for a long fin is given by this expression TB minus T infinity into square root of HPKA. For a short fin end insulated, TB minus T infinity into square root of HPKA multiplied by tan hyperbolic ml. So these are the expressions for heat transfer by the fin for different cases. Next, at the last we have, this is the efficiency of the fin for a short fin and end insulated, where m value is given by square root of Hp by Ka. Now, let us solve some of the numericals. In the first numerical, it is given that it is required to heat the oil to about 300 degrees centigrade for frying purpose. So we have some frying pan and we are going to heat the oil. A ladle is used in frying. So I'm just giving a screenshot of a ladle. The section of the handle is 5 mm by 18 mm. So that section, I've zoomed it here. So this is the 18 mm breadth and 5 mm this thickness. The surroundings are at 30 degrees. So surrounding, that is atmospheric temperature, giving it as, so T infinity written as 30 degrees centigrade. Conductivity of the material, that means the material, this material's conductivity is given as 205 watt per meter degree centigrade. If the temperature at a distance of 380 mm from the oil should not reach 40 degrees centigrade, that means if this is the base, from here I am taking 380 mm distance along the fin. That means from here to 380 mm along the fin. At this distance, if the temperature specified is 40 degree, determine the convective heat transfer coefficient. So we need to find the value of H at a distance of 0.38 meters. Since the length of the fin is not specified, we are assuming this to be a long fin. And what he has given, we have to find out. And since we know the temperature at a certain distance from this chart, we have to go for a long fin and the temperature distribution expression. So T minus T infinity divided by TB minus T infinity for a long fin is given as e power of minus mx. So we have to consider that expression from the data handbook and substitute the given data. So T, that means temperature at certain distance. And here what we have done is we are just taking the reciprocal of it. So getting it as TB minus T infinity in the numerator and T minus T infinity or Tx, both are same, Tx minus T infinity, that will be equal to, since it is reciprocal, it has come up as e power of mx. Now substituting the given data, TB is 300, T infinity is atmospheric temperature 30 degrees, and Tx, that means at a certain distance, that is 380 mm, that is distance. What is the temperature is 40 degrees. So 40 minus T infinity, infinite, that is atmospheric temperature is 30, that should be equal to e power of m. M value we do not know. Multiply by the distance x. What is the distance x? Is 380 mm. So in terms of meters, writing it as 0.38 meters. So if we simplify this expression, we get the value of m. But m, we know m equals square root of Hp by KACS. So that should be equal to, I'm just squaring on that side. We know the value of m. So m square will be equal to Hp by KACS. So H value, we do not know, keeping it as it is. Perimeter, what is perimeter? It is the at the cross section, sum of the lengths of this rectangular cross section. So breadth into height, that is plus breadth into height. So 2 times the breadth into height. So this is in meters, 0.018 multiplied by height, that is 5 mm, that is given as 0.005. So 2 times divided by K. K value is conductivity 205 and the area of cross section. What is the cross sectional area? 18 mm by 5 mm. So in terms of meters given. And finally, if we substitute, only unknown we get is H, and that we get as if we simplify, we get the value of H as 30.17 watt per meter square degree centigrade. Now, let us go for the next problem. Here, a carbon steel K of 54 watt per meter degree centigrade rod. That means this is a carbon steel rod having the conductivity with a cross section of an equilateral triangle. So here we are given, see here, this is the cross section having an equilateral triangle. That means all the sides have the same length of 5 mm, and this complete fin is of the length of 80 mm. This is attached to the plain wall, which is maintained at a temperature. This plain wall is maintained at a temperature of 400 degrees centigrade. So writing it as TB as 400 degrees centigrade. The surrounding environment is at 50 degrees centigrade. That means T infinity is 50 degrees centigrade, and unit surface conductance is 90 watt per meter square degree centigrade. So when you see this unit watt per meter square degree centigrade means it is the unit of H. So we are considering H as 90 watt per meter square degree centigrade. So we have written all the given data. Now they have asked to compute the heat dissipated by the rod. So we have to find out the value of Q. So heat dissipated by a rod Q. First thing before we do something, we need to know whether this fin is a short fin or a long fin. In order to check whether this fin is a short fin or the long fin, if it is not specified in the problem, you have to first get the value of m, multiply by the length L. If m into L is less than 5, we call it as short fin. If m into L is greater than 5, we have to consider it as a long fin. So if all the data available to find out the value of m, first thing we need to do is to find out the value of m. So what is m equals square root of hp by ka. So h, write h as it is. What is the perimeter of an equilateral triangle? This plus this plus this, that is 3 times this a, 3 times the 5 mm. So that 3a divided by k. K value, just substitute k value. What is area of cross section? Cross sectional area will be equal to half base into height for a triangle. So half base area A, base length is A. That is A, I am writing a 5. And this perpendicular, we have to find out this height h. How do you find the value of h? This by using a right angle triangle, and using the Pythagoras theorem, you have to find this height h. That is sine 60 degrees equal to opposite side by hypotenuse, and find the value. It get it, the opposite side we get as root 3 by 2. So if we simplify and then if we simplify, we'll get the value of m as 48.06 for this case. Now m into L. What is m is 48.06. Multiply the length. Length is 80 mm. So please convert it into meters whenever you solve any problem. So when we consider m into L, we get it as 3.84, which is less than 5. Hence, in this case, we have to consider it as a short fin. Now, considering this case as a short fin, now we need to find out what? We need to find out the heat dissipated by the rod. So, heat dissipated by the rod for a short fin, since these lengths are so small, we are considering as an insulated case, short fin insulated. So, Q equals, so use the data handbook, get the value of Q for a short fin insulated, and that value happens to be like this. Q is equal to root of HPKA into TB minus T infinity into tan hyperbolic M into L. Now substitute K value, conductivity, area, half into base into height of the cross-sectional area of a equilateral triangle, multiply by H, that is 90. It's all given here. Perimeter, 3 times the A is the perimeter, multiply by TB minus T infinity, base temperature. So base temperature is 400 degrees centigrade. So 400 minus infinity. T infinity means atmospheric temperature, given as 50 degrees. T infinity multiply by tan hyperbolic of m into L. So if we simplify this expression, you will get the value of Q as 9.823 watts. Now, Coming to the third problem. See here in this problem, it is given the aluminum square fins 0.5 mm by 0.5 mm. So this aluminum fins are 0.5, that means it's having a square cross section, right? Square fins. 10 mm long. So length of the fin is 10 mm long are provided on the surface of a semiconductor. So we consider this as a surface of a semiconductor. On the semiconductor, the fins of cross section, square cross section 0.5 by 0.5 with the length of 10 mm are attached to it. The temperature at the surface of the device should not exceed 80 degrees centigrade. So at the surface, that means at any point on the surface, the temperature should not be more than 80 degrees centigrade. When the surrounding temperature is of 40, that means atmospheric temperature is around 40 degrees. The average HTC is 15. So that means heat transfer coefficient H is given as 15 watt per meter square degree centigrade. Determine the number of fins required to carry out the above duty. See, since here in this case he has given what is the total amount of heat which is generated, it is 1 watt. And using this fin, we have to find out how many fins are required to carry or to carry this amount of heat which is generated. So first what we have to do is we have to find out what is the heat generated by a single fin. Then, so how many fins are required to carry out this, to remove this much amount of heat will be seen then later. So we have to find out, determine the number of fins. And he has given neglect the heat loss from the end of the fin. So end of the fin, we have to neglect the heat loss. Now, first thing what you have to do is, see these fins are provided, it's a short, if you just consider this, it becomes a short fin. Since I am not shown here, you can check it out. Get the value of first. We have to find out, first thing we have to find out, m is square root of hp by ka. H value is given. Perimeter is nothing but the length of the sum of the length of the four sides. That means 4a or 2 times this plus this. Both are same. 2 times 0.5 plus 0.5. This is in mm. So multiply by 10 power of minus 3 to get the perimeter. So h into p divided by k. K value is given, that is conductivity of the fin is 200. Area of the fin is, right, 0.5 into 0.5. That is area of the square cross section. Multiply by 10 power of minus 6. This is the conversion from mm to meters. So get the value of m. But then you can just even check. Multiply by 10 mm, you will get less than 5. So that means it is a short fin with insulated tip. Since he has given at the end there is no heat transfer from the fin tip. So now obtain the expression for the fin with insulated tip. As in the previous case, it is square root of hp ka into tb minus t infinity into tan hyperbolic ml. So that will be equal to, substitute the values, h value, perimeter we have found out perimeter, k value, then area of cross section, this is area of cross section of this, that is square cross section, then multiply by tb minus t infinity. Tb is the base temperature. Base temperature, he has given it as 80 degrees minus T infinity. T infinity is 40 degrees. Multiply by tan hyperbolic m into L. Tan hyperbolic, this is the m value, multiply by length value. The length is 0.01. So from this you can get it as we'll get the heat transfer from the fin. Now from single fin, this is the amount of heat transfer. So how do you find the number of fins? Number of fins will be equal to total heat which has to be removed divided by heat transfer from the single fin. That should be equal to total, how much amount you have to remove? 1 watt. 1 divided by Q of the fin. Q of the fin per individual fin. So you take it as, you will get it as around 85 fins. Now, the next problem is He has given a long fin of 12 mm square cross section. Again, this fin, same square cross section having 12 mm by 12 mm, made of, second, so 10 mm cross section provided on the surface, sorry, okay, made of low carbon steel, protrudes into air at 35 degrees. So at the air 35 degrees from the furnace wall at 200 degrees centigrade. The furnace wall is 200 degrees centigrade. Convective heat transfer coefficient of the material estimated as 22. So H is given as 22. Conductivity of the material is 51. So K of the material is given as 51.9. Determine the location from the wall at which temperature will be 60 degrees centigrade. That means from this point, you have to find the distance from where the fin temperature, that is X value, from where the temperature is 60 degree centigrade. Also, one more case you have to find out, calculate the temperature at 80 mm from the base. That means from here, you have to find out at a distance of 80 mm, what is the temperature. So both, there are two cases wherein you have to find out. In first case, you have to find out the length, and in the second case, you have to find out the temperature. Also have to find fin efficiency and effectiveness. Now, since he has already given long fin, so we have assumed it as a long fin. So assuming long fin, first thing what you have to do is we have to find the value of m. To get the value of m, you have to get the value of perimeter. What is perimeter? Perimeter is equal to 4 times the breadth. So 4 into breadth. You can also write as 2 times of this plus this. Both are same. Area. Area is 12 square, right? So area. Then m is equal to square root of h into p divided by k into a. You will get the value of 11.89. Next, what he has asked in the first case, he has asked location from the wall at which fin temperature is 60 degrees centigrade. So take this expression for an infinitely long fin. Temperature distribution equation, Tx minus T infinity divided by Tb minus T infinity equals e power of minus mx. Tx at a temperature at the x distance is 60 minus T infinity, Tb base temperature 200, T infinity 35. That should be equal to e power of minus m into x. X is the one we have to find out. M we have already found out. From this, get the value of x. That means at 0.159 meters, the temperature will be 60 degrees on the fin. In the second case, he has asked, find the temperature of the fin at x is equal to 80 mm. So at x is equal to 80 mm, that means T minus 35, because we have to find the temperature. So T minus T infinity is 35 divided by 200 minus 35 will be equal to e power of minus m value remains the same, multiply by x. X is given as 80 mm. So that is 0.08 meters. So simplifying this expression, we'll get the temperature of 98 degrees centigrade. Next, heat dissipated from the fin. How do you find the heat dissipated from the fin? Heat from the fin is given by, for an infinitely long fin, square root of HPKA into TB minus T infinity. So just substitute the values, H value, P value, K value and A value, area of cross section value, multiply by TB, base temperature minus infinity. So we'll get the Q as 14 watts. So maximum heat dissipated from the fin, Q max is given by, how much is the maximum heat into, that is, sorry, heat transfer coefficient H multiplied by perimeter into length, that is the area of area, multiply by TB minus T infinity. That will get it as 27.7 watts. So efficiency of the fin is given as Q of fin by Q maximum. So it is given as Q with the fin is 14 watts, Q, this is 27.7. So efficiency Q maximum is 27.7. So efficiency of the fin, we get it as 50% efficiency.